Okay, welcome to ECE111, Introduction to ECE. This is a walkthrough for homework set number 16. Now, week 16 we cover biomedical engineering. That's actually a very generic branch of electrical computer engineering. Biomedical engineering is engineering applied to people or animals. So in this case, we're going to be doing a modeling of the human heart using a Windkessel model. The Windkessel model is an RLC circuit that models the left ventricle. That's the heart pumping blood into the body, modeled as a voltage source. The left ventricle valve, RD1, a diode, so that when the heart pumps, the diode opens, I have low resistance. When the heart stops pumping, the valve closes, I have high resistance, allowing blood to flow out, but not back into the heart. The aorta is modeled as a capacitor. When the heart pumps, the aorta expands, absorbing the energy, or the capacitor charges up. When the valve closes, the capacitor discharges, kind of like the balloon squeezing down, pumping blood through the body. The blood has inertia, modeled by an inductor L2, and a little bit of resistance in the aorta. And then the body is modeled as a large capacitor, storing the blood, and a resistor, that's the blood going through the capillaries, coming back to the venous system. So that's the model. This homework set looks at, given different parameters for the heart, what happens under different conditions. First, how does the body behave under the nominal case? Second, what happens if I have a leaky valve? So that instead of RD1 being a high resistance, stopping the blood from flowing, the valve kind of stays open a little bit, allowing blood to flow back into the heart. The third case is a sticky valve. It takes a little bit of pressure to open up the valve, and then takes a little bit of backflow to get the valve to close. So there's a little bit of hysteresis there. I'm going to look at how does that behave when you model the system. And for diagnosis, I can look at the model and say, well, what does the simulation suggest if I want to diagnose, does somebody have a sticky valve or a leaky valve? What do I look at for the parameters, the pressures or the voltage, V1, V3, and the current? So to start out, I need to model the system. This is modeled by three coupled first-order differential equations. I have three ways to store energy, C1, L2, and C3. So the differential equations will be I equals C dV dt. The current I1 gives you the first equation. V equals L di dt. The voltage across the inductor gives you the second equation. And I equals C dV dt. The current I3 tells you the third. So let's go through the derivation of the differential equations. The current I1 is C dV dt. That's your V0 minus V1 over RD1, minus the current out, minus I2. So that's the excess current goes to I1, that charges up the capacitor. The voltage across the inductor is L di dt. This voltage is V1 minus I times R, V1 minus 4I2, minus V3. Then the current I3 is going to be the current in minus current out, I2 minus V3 over R3. So that's your three differential equations. In Matlab, I can then simulate that. So in the nominal case, that's the first problem. I want to simulate with a valve that's low resistance when the valve is on, V0 is greater than V1, high resistance otherwise. So Matlab I have a simulation. This is just giving an initial guess. What is the voltages V1, V3, the current I2? That's the energy in the system. The parameters. C1 is 2 millifarads. L2 is 50 millihenries, C3 is 1.5 millifarads, and RD1 is 1 megaohm. Assume the valve was initially closed. R2 is 4 ohms, and R3 is 220 ohms. And here's when we're storing the data. Now the way the simulation runs is, let's go through here. I'm going to go through 3 seconds of data, 1 millisecond per sample. And I'm actually going to sample 100 times faster. You need that because when the valve closes, I have this big snap delta function coming in. So I'm actually going to sample 10 times or 100 times faster. At each time point, I know the voltage. That's just a half rectified sine wave. That's the blue line here. That's V0. And here's my valve. That's what will be changing this homework assignment. Initially, if V0 is greater than V1, if blood is flowing out, the valve opens and RD1 is 0.1. Otherwise, it's high impedance, stopping blood flowing, it goes to 1 megaohm. Once I know that, I know the current through the valve. That's just V0 minus V1 over RD1. could be large if V0 is greater than V1, be very, very small, blood's trying to flow backwards. I now have the differential equations. These are the equations that I had from right here. So given the parameters, I can find dv1, di2, and dv3 dt. It's supposed to be dv1 dt, but Matlab doesn't like that notation, so we just call that the derivative of v1. Once I have that, I can now integrate. Moving forward in time, time moves forward by dt seconds, v1 increases by dt, vi2 and v3 all increase. Repeat over and over again. So this runs for 3 seconds, and if I run that, right up here, hit run, this is what I get. So what this is telling me, this is the pressure. The heart's pumping, that's the blue line. The green line is V1. Let's go back to the model. V1 is the pressure right at the outlet of the left ventricle, and V3 is the pressure at the body. That's your pulse. So going back, the green line is the pressure at the left ventricle. So as the heart pumps, the valve closes or valve opens, and the pressure follows the heart. As I start getting backflow, the valve closes. What happens, I have this little dip right here. You can kind of zoom in. If I can zoom in. I get this little dip on the green line. What's happening is the blood has inertia, so as the blood's flowing out, as the valve closes, it kind of pulls a bit of suction. That's the negative right here. And then it kind of rings out. That's an LC oscillator. That's on the pressure side. And then at the body, this is your pulse. I have the pressure goes up, then it comes down. Pressure goes up, then it comes down. So that's on the pressure side. On the flow side, the bottom graph, move this out of the way. Let's move this over here. On the flow graph, what happens is the blood comes out of the valve, that's the blue line, and then the blood at the body, that's the current through the inductor, the green line. Blood flows, and then it gets a little bitty backflow when the valve closes. At the body, that's just the LC oscillator. So that's the nominal case. And in terms of pressure, pressure goes from 100 to about 122 millimeters of mercury. Flow, there's some nominal value there. Again, nominal case. So that's the first problem. The second problem says, well, what happens if I have a leaky valve? Well, to model a leaky valve, go into Matlab. What I do is I go back up here. This is where the valve is. When the valve is open, it's 0.1 ohm. When the valve is closed, it's very, very large. That prevents blood from flowing. V equals IR. I is V over R. Large resistance means low flow. If I make this something small, like 50 ohms, what's going to happen is the blood flows out when the heart opens, but it doesn't block the flow all that well. I get a little bit of flow, the valve's kind of staying a little bit open. That's a leaky valve. What happens if you have a leaky valve? Well, in the simulation, I can run it. That's the nice thing about simulations. I can sit there and run this, and I'm not doing any damage to a person because this is all software. I can do what-if situations. And here's what you get. I just ran that simulation, and what it looks like, let's expand that out a little bit. The top graph is pressure. Again, the blue line is the heart pumping. The heart puts out a pressure and then waits for the next heartbeat. Not exactly what the heart pressure looks like, but this is just kind of a model to give you an idea. The green line is the pressure at the left ventricle. Again, when the valve's open, it follows it almost exactly. There's only 0.1 ohm between the pressure and the left ventricle pressure. The red line is the pressure in the body. Now prior, the pressure went from about 122 to about 90. Now with the leaky valve, the pressure drops all the way down to about 50. What that does on flow is actually have negative flow. So when the heart's pumping, I have blood flowing out, that's the green line. And then over here, I actually have blood flowing back into the heart. I have negative flow. So the net flow will be more negative. And also if you look at the peak, this was about 1100. If I go back to the previous case, the flow peaked out at about 600. So what I have is the heart's pumping much harder. I'm pushing out more blood, and then more blood's coming back in. Pushing out more blood, then more blood's coming back in. There's much more blood flowing back and forth through the valve. So if I wanted to diagnose this, what I would do is if I have a huge amount of blood going back and forth, that's probably an indication of a leaky valve, or this black backflow right here. If blood's actually flowing back into the heart, that's a leaky valve. Another way to diagnose it, if there's a huge change in pressure from the heart ejecting to the bottom, that huge change is another symptom of a leaky valve. It's something you can see from the RLC circuit. You don't actually have to experiment on people to find this out. The third case, what happens if I have a sticky valve? And in Matlab, I just changed one line of code. I go back over here, here's the valve. This is an if then else. Either the valve is open or it's closed. That's a normal valve. A sticky valve would actually have two if statements. The first one says that if I have enough pressure to open up the valve, it turns on. And in this case, actually, I need 1 volt to turn on. Where are you? There you are. So V0 minus V1 is greater than 1. I have more than 1 volt pressure, then the valve opens. Conversely, to close, it takes a little bit of negative pressure to get the valve to close. So instead of an if then or an if then else statement, I just do two if statements. And here this is going to be a good valve. You could also do a leaky valve with stiction. Just to keep things simple, I'm going to vary one thing at a time. I have either the valve opens or closes. Now in between, if the first case fails and the second case fails, what happens is RD1 remains at whatever it was. So if it was open, it stays open. If it was closed, it stays closed. That gives a hysteresis slope. It takes a little bit of pressure, 1 volt to open up the valve. Then it stays open until I get down to minus 0.3 volts. So let's see what happens if I run that case. So here's what we had before. If I now run the case with stiction, static friction, or hysteresis in the valve, this is what I get. So what's happening on the top graph is the valves closed, valves closed, valves closed. I have the heart pumping. It's not going to open until I get 1 volt pressure. That's right here. Now let's zoom in on that. So right here, as soon as you get 1 volt pressure, the valve closes, the valve opens, and now it's 0.1 ohm. It stays open until the pressure drop becomes negative 0.03. At that point, the valve closes. When the valve closes, I get kind of a big snap. There's a little bit of backflow because the valve was open briefly when the pressure in the body was more than the heart. That's this area right here. And then once the valve closes, I get rid of the backflow. That shows up on the flow diagram as well. Let's zoom in on that. So again, the valve is closed. As soon as you get 1 volt across it, these aren't quite synced up. As soon as you get 1 volt across it, I suddenly have the valve open, and there's this big splurt of blood. Well, that's because I have the valve suddenly opens. Actually doesn't do that all at once. It takes a little bit of time to open up. But with this model, it's either bang on or bang off. Here I get this big spike due to the bang on. The blood flows, and then at this point, I have actually negative flow. That's the sticky valve. I get a little bit of flow, blood flowing back into the heart while the valve is open, and then with a little bit of flow or pressure, it then closes. So here's the brief influx of flow back into the heart. In terms of diagnosis, if I had these measurements and I want to detect what's happening, again, the pressure looks good. I've got 120 going to about 100. The flow looks fairly reasonable. Right here, however, I'm getting a little bit of backflow into the heart right after the valve heart's done ejecting. You can see that right here, I get a little bit larger of a blip. That's kind of an indication of a sticky valve. So that's kind of some of the things you do in biomedical engineering. You're trying to model the heart using electrical analogs, and that actually has quite a bit of implications. For example, as we talked about in this homework assignment, I can use this for diagnosis. If I get certain measurements, certain waveforms, that tells me what's happening in this model. That tells me what's happening in the person. On the other hand, if I want to say, well, certain parameters are good, what drugs affect C1? What drugs affect R2? What drugs affect L3? I can then start tailoring drugs to adjust how the body behaves. If the body has some ailment so that one of these parameters is off, how do you adjust that parameter? Opens up a whole new area for drug research. That's some of the things you do in biomedical engineering, but here's using an electrical analog to help understand what's happening in the body. That's kind of a walkthrough for homework set number 16 for ECE 111.